Great. Hi everyone, welcome to This Week in Space Science. I'm Michael Baltimore, your host here. And of course, we wouldn't have a show without this gentleman to my left. This is Dr. Sean Cruzen from the Coca-Cola Space Science Center. That lower third was actually not his, but that's okay too, because here's what we're going to do on this show today. We're going to talk about the year of the comets, 2013. This is the year of the comets. Sean? Yes. Tell us a little bit about why this is the year of the comets. There must be so many of them coming our way, right?
Well, what's amazing about this is there are several bright comets that are going to be visible from the Earth, from the northern hemisphere even, during the year of 2013. Now, comets are not that unusual. There are oftentimes several comets in the sky that can be found either by professional astronomers or by amateur astronomers with fairly large telescopes at any given time. However, this year, there are going to be 3 comets that are very, very bright. Some of those in the near future, one of those in the fall. All 3 are worth talking about, and actually comets just kind of get me excited. They're a very interesting object to be observed in the night sky. So I've kind of dubbed this 2013 as the year of the comets for the show today.
Oh, I like it. Well, I tell you what, we need to start with kind of a definition of comets. And you know, one of the things, you might be right about 2013 being the year of the comets. I think we're seeing more of these on the news. I mean, it seems to make the news more now, and I'm not sure if that's a phenomenon that is just happening because we're covering it more often, but they seem to be in the news a lot. So yeah. Start with telling us what is a comet. Rock and ice?
Yeah, we can talk about what comets are and where they came from, and you're right. So it's different from an asteroid. Okay. In the sense that a comet has a lot more ice in it. Now, asteroids and comets, they're certainly cousins in the space junk category of objects just kind of flying around through our solar system in various locations. So you can think about them, they're not planets, they're not moons, they're smaller than that even. But they're very large compared to something like a meteorite, something like a rock that we would normally consider falling in from space that might land in your backyard, hopefully not, but some kind of a meteorite that would come through like that. So they're in a category where they're anywhere from tens of miles to hundreds of miles in size, generally. So the difference, though, between the asteroids and the comets is that comets tend to come from a place that's much further out in the solar system. And obviously, the further away from the sun that you get in the solar system, the colder it is out there. The colder it is out there, the more substances can be frozen to the surface of these bodies. So things that we normally think of as gas here on the surface of the Earth, compounds like carbon dioxide and carbon monoxide and this weird stuff called cyanogen and nitrogen and methane and ammonia. Generally, we find these in either liquid or gaseous form. Okay. At the place where comets are usually found in the solar system, it's so cold out there that they freeze solid to the surface. So now you have this body that is in part rock and dust and dirt, but it's far greater composition of water ice, H2O, but also all these other ices of these frozen gases and frozen compounds like carbon dioxide and the rest.
Okay, so where do comets come from? You said they are sort of far out in our solar system.
They are today, and so the solar system that we live in today, we find what we call these volatile compounds. Volatile just means when you heat it up, it tends to turn to a gas very fast. Those kinds of compounds can exist in the inner part of the solar system. They exist better farther from the sun. So the place where we find them in a solid form is in locations well beyond the orbit of, say, Neptune, or maybe even out beyond Pluto, in these various zones that we find out well away from the sun. Now, that's where they are today. It's not necessarily clear that that's where they were in the early part of the solar system. So when our solar system was in formation, these kinds of bodies with these volatile compounds on them could have been flying all through the inner part of the solar system, and very likely were. And so we think that a lot of the volatile compounds that we find on Venus, Mars, and Earth, all 3 came from impacts with these cometary bodies in the very early part of the solar system. But here's where we find them today. So if you think about the solar system and what it looks like, it looks like a kind of a plate or a disc, a frisbee, for lack of a better term.
Right. Okay.
And so in that plane, which is known as the ecliptic plane, almost all the planets are neatly in that plane. A few dwarf planets like Pluto are kind of coming up out of that, but the rest of the planets march pretty neatly within that plane. Well, in that same disk further out, there is a belt of cometary bodies, these small ice balls that we call the Kuiper belt. And so we can find that Kuiper belt out beyond the orbit of Neptune, even mostly out beyond the orbit of Pluto. However, Pluto does kind of cut through that belt at its farthest point from the sun. But this is just a whole range of cometary nuclei, these ice balls that are out at the outer part of the solar system. You might ask, how do we know? How do we know they're out there?
Good question.
You might ask that.
Well, I would. But
okay, but I already set it up.
So
That's
we're going to go with that.
so since you asked, we're going to talk about why we know that's true. There are, as comets come in, there are a group of comets that come in with orbital periods and orbital parameters that place them about at that distance of the Kuiper belt. And they tend to all come in the plane of the solar system. So they're not coming in at odd angles. They're not coming in 90 degrees to the rest of the planetary orbits, things like that. They tend to come in right in that plane, and they come in these ellipses that their farthest point from the sun would place them out in this range that we think that this Kuiper belt exists out there beyond Pluto. So since so many of those comets come in, there must be a source of those comets out there. And that source of comets out there is thought to be this Kuiper belt that exists out beyond the orbit of Pluto.
Now, you talked about orbit. So
yes.
This Kuiper belt that's on this plane, are they orbiting the sun?
They
like
are.
Planets
they are. And they tend to be in what we would think of as kind of circular, stable orbits. So they're not crisscrossing through the inner part of the solar system for the most part.
Right.
They're out there minding their own business. They're out there at a very big radius from the sun in an almost circular set of orbits out there. That they're very stable. And the reason they have to be very stable is if they were around since the early part of the solar system, they can't be making close passes to the sun or they would have melted by now.
Right.
But the dynamics of the situation occurring out there in that belt is that sometimes these little comet bodies get close to each other and they either bump each other or they disturb each other with their relative gravity, and one gets pushed out and the other one gets pushed in. And the one that gets pushed in literally can kind of tumble and fall into the inner part of the solar system. And so that's why once in a while, then we get a comet from that sort of range that comes in and sweeps through.
I was wondering, it sounded like it was pretty stable out there in an orbit like planets are.
It is indeed. It is indeed stable for the most part.
Unless they get tripped to hit or bumped and get out of it.
It's just thought that there's so many of them out there they can dynamically affect one another.
All right, so how big are these comets?
So comets tend to range in size for anywhere from, maybe say 10 miles or 20 miles across, all the way up to a couple of 100 miles across. 300 miles across is the biggest comet that's ever been identified. And that's certainly a rarity. But these comet nuclei, they kind of look odd in shape. They're so small that they don't have enough gravity. They're not sufficient gravity enough to pull themselves round.
Okay.
So they have these kind of potato-like, odd-looking structures to them. Right. And so if you could actually get in close enough to see the nucleus of a comet, you would see it having that kind of a structure. I think we have a photograph of these two comets that are sitting next to one another. And it's a great example because there was actually a spacecraft called Deep Impact from NASA that got in close enough to these comets to photograph them. And so we have really good, sharp images of these cometary nuclei, which gives us a very good look at what they look like.
And I assume we can measure that. There's some way that we can actually measure those as they come out in space.
Once those comets are photographed, the scientists who are on the project, they know the distance to the comet and they know their image scale, so they can use that to find the size of those comets out there. And again, they tend to be, maybe say 20 to 50 kilometers across on that order.
All right, let's see if Elmo can run through those slides for us real quickly, and let's see if we can find those.
It's a great shot, and again, one comet is called Hartley 2, and this is actually, in fact, a shot of Hartley 2 right here. So again, you see that it's very potato-shaped. Now, this is a smaller comet, so it's really elongated. It kind of has two lobes. You might see that material coming off of that. That's called outgassing.
Well, I was just wondering, is there light behind it shining? Or
there is. So this is photograph taken with a little bit of sunlight behind it. So the sun's not exactly directly behind it, but it's off and to the right, if you can imagine, kind of on this shot right here. And it's lighting up that material coming off. Well, those are jets of gases that, as this cometary nucleus gets close to the sun and begins to melt, it doesn't actually melt into a liquid form.
Okay.
it does this process called sublimation, where these solid materials turn directly to a gas and they jet out explosively. They just actually literally blast out from the cometary nucleus.
Okay, now this is the slide you were referring to.
So this is the photograph I was telling you a little bit before. You can see how much smaller Hartley 2 is than Tempel 1. And the scientists on that Deep Impact project put these two cometary nucleus together so you can get kind of a size comparison. Tempel 1, a much, much larger comet.
Oh, absolutely.
Gives you just a sense of scale that how much of these things can vary. Also looked at Tempel 1, even though it's not round, it's much more round in shape than Hartley 2, and that's because it is bigger, it does have more gravity, and it does, even though it can't pull itself to a perfect sphere, it does pull itself into more of a spherical shape in general.
Let's talk about that just for a moment, because we were, before the show started, we were talking about sort of the formation of planets in our solar system and those kinds of things. And so if from the little bit of research and viewing that I've done recently, it talks about the formation of a planet coming from all of these asteroids and rocks and ice and other objects that are flying around, and at the formation of the solar system, all of these rocks started to come together, and they would kind of bind together.
They would indeed.
And then there would be more of those, and at a certain, I guess, size, diameter across, they would look more spherical. They would become the planets that we come to know now.
That's right.
Is that true?
That's the model that we understand of the way a solar system forms. And again, so think about it. The solar system actually comes from these big clouds of hydrogen gas that have a lot of dust and a lot of ice inside of them. Something sets off a process by which these clouds collapse. The most dense part of the gas is obviously in the center. That's going to become a star.
Okay.
And then so in the process of formation, we call that a protostar.
Okay.
And the cloud also begins to spin. So as the cloud spins, it kind of resists collapse in the plane that it's orbiting in. It's kind of like spinning a rubber band around with a ball on the end. The ball tends to pull the rubber band out. Right. So in the plane that it's spinning, it resists the collapse. But in the other dimensions, it just collapses right down like a pancake.
Okay.
So you go from more or less a spherical cloud to the spinning disk.
So like on a plane. So
on a plane,
it's
exactly.
of a disk like.
Yeah. And that's exactly why we see our solar system looking like that today.
And so these are rocks and clouds and gases and other kind of things spinning around.
That disk is now just full of these materials like you're describing. It's little particles of ice, little particles of dust and rock that begin to stick together.
Okay.
You see, once you've formed a coat of ice on the outside of a particle, it's kind of sticky.
Right.
So the icy materials, like a snowball itself, when you roll a snowball across a snowy field, that stickiness in the snow tends to gather more of that material up. Well, that's the same thing that's happening in that disk. It crunches down, those materials stick together, it starts to grow. As that object grows, it has a little bit more gravity, so that it can begin to pull in more materials. As more materials stick, it grows, it grows. It's kind of like now rolling a big snowball downhill.
Right, okay.
It's gathering more and more material until ultimately it gets to that threshold that you were discussing, which is somewhere between 500 and 1,000 kilometers in diameter. This thing can now pull itself into a spherical shape because it has sufficient gravity. There's enough mass there that the gravitational forces can pull itself into more or less a spherical shape.
Okay.
Once it gets to that point, we call that thing a protoplanet.
Okay.
So before these little chunks of stuff, we call those planetesimals, but as they stick those all together, they form this big round ball called a protoplanet. We have long postulated that the comets in our solar system are just these leftover planetesimals that are way out at the outer parts of the solar system, and that protoplanets formed, and then they even collided and did things like form the moon and various other processes in our solar system.
Sorted themselves out, but then there's this huge belt of these that didn't form.
They're far distant. The neat thing about that is we can now, with our telescopes like Hubble Space Telescope and some of the better telescopes out there, we can now look at other solar systems well enough that we see that same process of formation taking place around stars such as a star called Beta Pictoris. There's a star called Beta Pictoris out there that is just one example of many of these other kinds of solar systems in formation that we've been able to observe.
Okay, with all of those things that are spinning around in that disk type shape.
Exactly.
All right, so these comets are on the outer of our solar system, on the outer edges of our solar system, and they bump into each other, and all of a sudden they may be thrown toward a planet, and then if the gravitational force of some of these these planets in our solar system might pull those toward them.
Yeah, exactly.
And that makes it a little dangerous, I assume.
So once these comets disturb and they're just randomly flying through the plane of the solar system, now all of a sudden it's a bit of a shooting gallery, right? So you have these objects flying in at high speed. Obviously, the planets are on their stately orbits in the interior of the solar system as well, including some big planets like Jupiter and Saturn, but also planets like Earth and Mars and Venus in the interior part of the solar system as well. And what happens is, as these comets come through, most of the time, almost all the time in fact, they glide through that solar system without much problem.
Right.
But occasionally, in the past, they've either gotten close enough to the sun where the sun's gravity can pull them apart, or the heat of the sun just causes them to break apart, or they've actually occasionally impacted the planets in the interior part of the solar system, even the Earth. And so there's a mass extinction that took place about 12,000 years ago, where in the geological record of that time, we're now finding these little nanodiamonds in that geological layer. And these little nanodiamonds are a signal that possibly some kind of a large impact from space occurred about the same time that mass extinctions of certain species were recorded in North America, at least anyway. So, could have a comet impacted at that time and possibly been tied to that mass extinction? The thought is that maybe yes, maybe that occurred.
Right.
And so obviously that's just one example of a history of the planet Earth that looks as if it's been impacted many times by not only asteroids and large meteors, but also by comet bodies that carry a lot of these volatile compounds with them.
Wow, they're out there everywhere.
There's a great story we have to tell here too, and it's a quick story, but in 1908, something that had a lot of icy material came in over Siberia, a place called Tunguska, over the Tunguska River area, and exploded. It detonated, and as that object detonated, it literally leveled 850 square miles of forest. And so that object was not like a rock because it didn't actually hit the ground. It blew up in the air, it exploded over the ground and just leveled trees in all directions. And so that would have been more like a comet nucleus, or if it wasn't a comet, it was an asteroid with a lot of volatile material in it. Okay. And so this is something that's like a comet that, again, in recorded history, in recent history, did come in and impact the Earth. So obviously impacts of these bodies is something we have to think about. Back in 1994, there was an incredible event that took place. The planet Jupiter grasped onto a comet that was later known to be known by the name of Comet Shoemaker-Levy 9. And it actually pulled the comet apart. That's the tidal gravitational forces of the planet Jupiter ripped this comet into about 21 pieces. And there were 18 major pieces. And so as these 18 major pieces were captured by Jupiter's gravity, they started to orbit Jupiter rather than the sun. And they did that in a way that was a decaying orbit. So they kind of spun around Jupiter for a while, like soap going down a drain. And then all of a sudden, one by one, they began to impact the surface of Jupiter. Now, scientists knew that this was going to happen. They had discovered this comet, and they saw these pieces falling into Jupiter, so they predicted the time when it would occur. And when I was a mere graduate student out at University of Nevada, Las Vegas, I took a telescope out into the desert and I watched as the first one of these comet chunks impacted Jupiter.
Okay, all right.
It hit on the backside,
all right,
so we didn't see it, but then as it hit the planet and the planet Jupiter rotated around, Jupiter suddenly had a giant black eye in its southern hemisphere. And you can see by this photograph right here, these are all zones, these are all regions where various chunks of Comet Shoemaker-Levy 9 exploded in the atmosphere of Jupiter.
Well, now, we're not talking small comets either. What are the size of these?
Well,
and then it says it was one, but the gravitational pull pulled it away.
Exactly. So you can see in this photograph right here, now what you have is over a dozen mini comets, right? Okay. So this was a fairly large size comet, but all of those fragments were on the order of 1 to 5 to even 10 miles across. And as they came in, they are full of, again, these volatile compounds. They hit Jupiter's atmosphere, which is itself a gaseous atmosphere, but there was all kinds of friction which rapidly heated that material, and it just exploded like a hydrogen bomb and literally left these mushroom cloud-like features in the atmosphere of Jupiter, which we saw as kind of black in color. Now, you might ask, well, why are they black? That seems sort of weird. You'd think they'd be whiter, brighter, or something like that.
Right.
And it's because of the kinds of chemistry that was taking place in those explosions literally turned that material into a kind of a sooty, tarry, black looking color and gave Jupiter a whole lot of black eyes.
Wow. Well, I may say I'm glad it was Jupiter and not Earth.
You can imagine what might have happened on the Earth if you recollect that picture where we saw those big black eyes on Jupiter. Each one of those was approximately the size of the Earth.
Okay.
So just those scars in the atmosphere of Jupiter, about Earth-sized. So imagine one of those chunks then hitting the Earth. Well, you can see that these are very, very large explosions. Those chunks hitting the Earth would have done major damage to the planet. So Jupiter actually sort of acts like a gravitational protector out there in the more distant part of the solar system. Because of its large gravitational field, it pulls these bodies in, and it kind of plays goalie in a little bit of an analogy. It's blocking some of these particles from the outer part of the solar system from coming in here to the Goldilocks zone, the habitable zone inside, closer to the sun, where we live, and it blocks those objects out and pulls them in before they have a chance to impact on the Earth.
Oh, thank you, Jupiter.
Yeah, exactly. Right.
All right.
It's very, very true.
All right, so we've got some other comets to talk about. So what about this comet Lemon?
So there are 3 comets that we're going to talk about today, and if you start out with a lemon, where do you go from there?
Yeah, there you go.
Well, Comet Lemon, it's actually 2 M's on lemon.
Okay.
So Comet Lemon is based, the name of it is actually based upon a survey being done at Mount Lemmon Observatory run by the University of Arizona. So they're using their telescope at Mount Lemmon to scan the skies to find these kinds of objects that come through. And so once they find that with that sort of a survey, usually the comet is named after the survey that was completed that located that comet. So this is now Comet Lemon. Comet Lemon is in the southern hemisphere right now. It's a beautiful looking photograph. So this was a photograph that was up on the space websites here in the last few days. I pulled this one from spaceweather.com.
Okay.
This is a photograph taken by a gentleman from New Zealand who photographed the comet. Absolutely gorgeous shot of a comet right there.
It really is, isn't it?
And the neat thing to know is the reason we're talking about Comet Lemon is because it's going to be visible from the northern hemisphere in early April, possibly to the naked eye. So this thing is going to brighten as it continues its path around the sun. It's going to continue to get a little bit closer to the Earth. It's going to move in a position where it's going to be visible from the northern hemisphere of the Earth. And hopefully, those of you who have telescopes or binoculars, you can take your telescopes and binoculars outside in your own backyard and watch for Comet Lemon and be able to see it. But maybe you'll even be able to see it without the aid of any kind of optical instruments at all. That's how bright it could potentially get. So this is a really exciting thing. And if we just had one of those kinds of comets in a year, I personally would be very excited.
Yeah, that's a big deal right there.
But remember, this is the year of the comets.
Exactly.
2013.
Must be another.
There must be another.
There must be another.
And there is. We're going to talk about it right now.
All right,
so the next one we're going to talk about is called Comet Pan-STARRS. That's a weird name for a comet.
Yeah, it really is.
There's no individual person named Pan-STARRS, by the way. So Pan-STARRS is a survey that's being done in Hawaii. It's called the Panoramic Survey Telescope and Rapid Response System. Pan-STARRS.
Now it makes sense.
But what it is, it's a very wide field telescope. Here we're seeing a shot of it, beautiful looking observatory dome there.
Oh, yeah.
A very wide field telescope with a huge camera with a giant CCD array that allows it to observe very vast swaths of the sky. This survey instrument can actually photograph the entire sky in great detail in just 1 month. And so that kind of a total sky survey is the perfect sort of instrument to be able to find new asteroids, new comets, new space junk that has yet to be identified, and other things like supernova going off and things like that. So, so Comet Pan-STARRS,
it's a good looking scope, isn't it?
First identified this particular, it is a great looking scope. I'd love to go see that actually.
Love it. It'd be nice.
Comet Pan-STARRS, the Pan-STARRS telescope first identified this comet. It is also in the southern hemisphere. It's also moving north, and it's going to be visible in the middle part of March. Now, it likely won't get to that naked eye visibility, but it should actually be visible enough to easily be seen in a pair of binoculars or in a backyard telescope in the month of March, about mid-March. Now, it's doing something kind of amazing. It's passing very, very close to the sun. It's going to pass closer to the sun than the planet Mercury, only about 3/10 of the distance that the Earth is from the sun. And here we're seeing a calendar of what you can expect to see from northern hemisphere locations. If you look to the west just after sunset, you'll see the comet in those positions throughout the month of March. Those numbers right there on that calendar correspond to dates.
All right.
So if you look up there and see on the 13th, there's a little crescent moon right under the 13th, March 12th and 13th. That's where that comet's going to be relative to the moon on March 12th and 13th. And so that's going to be an easy indicator to help you find that comet in the sky.
That'll make it easy for us, right?
And so the other interesting part is this comet will have just made its nearest pass to the sun on March the 10th. Well, that's when it's closest to the sun, is when it heats up the most, it's when it melts the most, it's when its tails grow the largest, and so that should be the easiest to see once it passes that point of nearness to the sun that we call perihelion, its closest point to the sun. Once it passes that, it should kind of explode in size and be better visible after the 10th of March.
From the 10th up and then the 13th with that crescent moon.
Yeah, throughout the rest of the spring months, we'll be kind of watching that comet. That'll be a very exciting target for telescopes out there.
Something to look for, and in this year of 2013, the year of the comets.
The year of the comets.
Now, we talked about 2 so far. Did you say there was another?
There is a third one, and actually the third one is kind of the cream on top of the pie here.
All right,
because
let's hear about it.
It is the piece de resistance of this particular vanguard tour of comets here.
Tell us about it. What's the name
It's called
of this
Comet
one?
ISON.
Ah, there you go.
Comet ISON. Of course, ISON, another acronym, stands for International Scientific Optical Network. This particular telescope that was part of this network that photographed the comet first was in Russia. So some Russian astrophotographers were the first one to record and identify this comet. But this comet, here's the photograph right here of it. This was actually a photograph taken just a couple of days ago. But this comet is right now, as we film the show, about at the distance from Earth to Jupiter. And yet it's already showing up on photographs. Now Jupiter's 5 times further from the sun than we are. So this thing's really a long ways out there. It's not going to get to the inner part of the solar system until the fall. Really, it's not going to be best viewed until about Thanksgiving time of 2013. But at that time, this comet's going to do something amazing. It's going to sweep by the sun at a tremendously close distance. It's literally going to dive right through the outer atmosphere of our parent star, the sun. It's going to pass just 880,000 miles from the sun's surface. And it's a big comet. So it's a very large comet. It's going to pass very near the sun. When that happens, if this comet survives its near pass to the sun and makes it around the other side, what's going to come out the other side is all kinds of material that will be shed by this extremely close pass with the sun. A giant tail. You're going to see a huge coma around the head of that comet. You're going to see all kinds of material coming off of it. It could be reflecting so much sunlight back to the Earth that this comet might be bright enough to be visible in broad daylight.
Okay.
That's a tremendous comet. And so I've seen many comets during my history as an astronomer. In fact, I came to Columbus State University in 1997. That was the year of the Great Comet of 1997. A lot of people know that one as Comet Hale-Bopp. And it was that kind of twin-tailed comet that a lot of people have seen when they look at these pictures online and things. But Comet Hale-Bopp would have been an amateur compared to what Comet ISON might be. Because Comet ISON, it could literally stretch tens of degrees across the nighttime sky. But its head could be visible in daylight. And here we're seeing Hale-Bopp, by the way. Hale-Bopp was a fantastic comet, extremely bright. I could easily see it in the bright lights of downtown Las Vegas. But here you're seeing 2 tails, the blue tail that's kind of jetting from lower left to upper right. That's what we call the plasma tail or the ion tail. That's gas streaming off. And then you see that kind of white tail streaming out behind the comet. That's the dust tail, and the dust tail is actually formed of heavier materials, and it's reflecting sunlight back, so it looks a little bit kind of yellowish white right there. But in fact, the comet's probably moving to the upper left in this photograph because it's going around the sun, and the sun is in the opposite direction of that blue tail, as you see here in the photograph. So there's a lot of physics you can find out by just looking at these images of the comets. You know which way it's moving, you know where the sun is in the sky, things like that. But the interesting thing about this one is the Comet Hale-Bopp came right over the top of the sun, and so it really split up those 2 tails in a way where it became kind of a prototype for an example for showing off those 2 tails. Will Comet ISON look like that? Well, Comet ISON is not coming directly over the top of the sun, but Comet ISON is going to be so dramatic that tail, those tails that you saw from Hale-Bopp right there, they could literally drift and span half the visible sky and be seen bright enough to be seen in twilight hours as the sun sets. So the head of the comet visible in broad daylight, the tails of the comet visible in the twilight hours. It could look something like this just after sunset in the months of November into December
That is
of
extraordinary.
2013.
That is extraordinary. And it's going to come so close to the sun, and the sun's gravitational force and the force of the sun is going to have a big effect on this as well, as you said. Right?
Certainly the sun will slingshot it around, and that's why it's passing through so rapidly, because of that tremendous gravitational force you were discussing. But then as it slingshots it around the sun, it's also very close to that heat source, and it's going to be melting it like crazy. We don't know what the interior composition of that comet's really like. We don't know how stable that cometary nucleus is. Will it break apart?
Right.
Will it hold together? What will happen? It's a big mystery. And that's one of the things that makes this kind of stuff very, very fun to be able to watch.
Well, it's going to be a dazzling show in any case.
It should be spectacular.
Around November 2013. So that's the time to look for this.
It is. And so we'll begin to see this comet in the earlier months of 2013, probably earlier in the fall. We'll begin to have a target that we can observe from the Space Science Center. It'll be in the morning sky. But then as it passes the sun, it's going to whip around to the evening sky, and that's when all the real excitement happens. That's going to be on or around the 28th and 29th of November. So again, I kind of called Thanksgiving right there. It's going to be a little bit later than that. 28, 29 of November in 2013. And we just don't know what's going to happen. And that's, again, that's what makes it fun. When you have a mystery like that, when you get to watch a situation like this evolve and you really don't know how it's going to come out, that's when science really takes place, because you can try to factor in all the physical parameters that you know about and that you understand about these objects, but really they're more complex than you can put into a set of parameters, so we just don't know. And it's really fun to watch this evolve in real time out there in the solar system.
It's absolutely amazing. You call this show the Year of the Comets. This is the show of the comets in 2013 as well. You've talked about Comet Lemon, Comet Pan-STARRS with an S on it, and Comet Ison. Okay, we can't wait to see what happens with this. Thank you so much, Sean, for bringing all of this in and talking about it today and helping us understand what comets are, where they come from, and what happens after that. So, again, another great show, and thank you very much for being here with us.
You're welcome. Thank you.
Hey, thank you guys for tuning in. This has been This Week in Space Science. I'm Michael Baltimore with Dr. Sean Cruz, and we'll see you next time.